Lecture number 3, Units and Dimensional Analysis. So in this lecture we're going to talk about the 7 fundamental or systematic units we have in chemistry, and then how we can convert between those separate units or magnitudes of those units using a process we call dimensional analysis, or a standard method to do these calculations. So the first one of these 7 SI units is for mass. So the base unit for mass is the kilogram. A couple notes about mass. We've already talked about the difference between mass and weight in class, where mass is a constant amount and weight is variable depending on the amount of gravity pulling on it. So 100-gram mass here on Earth will weigh less on the moon where it has less gravity, but its mass will be the same. A couple interesting things about mass. It's our only SI unit that's based on an actual physical object that's kept in France, and it's the only one that has a prefix in its base unit. So the base unit of mass is the kilogram, kg. Our second unit is for length. The base unit for length is the meter. And this meter's been standardized by the speed of light in a vacuum. As you can see here, that's the way we measure that, that fraction of a second it takes light to move that 1 meter. The third unit is for time. The base unit for time is second, and it's based on the atomic clock. It's the property, it's fixed, it's fairly constant, and that's also, in fact, kept in France. The fourth unit is for temperature. The temperature here is in Kelvin, abbreviated capital K. Note that on capital K, Kelvin, there is no degree symbol as opposed to degrees Celsius or Fahrenheit. This is because Kelvin is an absolute scale. It goes from 0 to larger numbers much larger than 0. And we can convert between the units we typically think of, the Celsius unit, to Kelvin by adding 273.15 to those Celsius units to get to Kelvin. And we can convert from Celsius to Fahrenheit or Fahrenheit to Celsius using this equation where we take 9/5 of the degree in Celsius and then add 32 to it. So we have these, but please note that this absolute scale for temperature is in Kelvin, with no degrees symbol. The fifth one is electric current. We'll talk much more about electric current in much later chapters. I want you to be aware of the SI unit for that. It's in amperes, capital A. And we'll come back to that probably a lot in great detail at the end of next semester in 112. But right now, just want you to be aware of it. The one we're going to spend a lot of time talking about this semester is the amount of a substance whose base unit is the mole, M-O-L. Like I said, we'll spend a lot of time about defining what a mole is and do the conversions between those starting in chapter 3. But it is one of our 7 base SI units. And the last one is the base unit of candela for luminous intensity. We're not going to talk much about this, but it is one of the 7 units, so you need to know it. All of these SI units are in the metric system, which means they're based on factors of 10. So if we think about the meter, for example, 1 meter, then go to 10 meters, which can abbreviate decameters, which would be DAM. We can go to 1,000 meters, which would be kilo. So if we go to 1,000, that's kilo. 1,000,000 is mega. If we go smaller than that base of 1 to 1/10, that is a deci. To 100th, that's centi. To 1,000th, that is milli. And then we can go down further to millionth, which is micro, and then a billionth, which is nano, and then this very small unit of pico, which is 12 places, 12 zeros before the 1. So we have a shorthand. As you can see, once we get to the extremes of these measurements, we get a lot of places, very big numbers or very small numbers. We've come up with a shorthand notation to signify those numbers, make them easier to read and easier to write. by using this scientific notation. We're putting one unit in front of the decimal place and then sort of giving an indication of the magnitude by raising that number times 10 to whatever. So we can see with mega, where we have 6 zeros, that would be 1 times 10 to the 6th. If we go down to micro, which is 1/millionth of 1, then it's 1 times 10 to the negative 6. So depending on which way, if it's bigger than 1 or less than 1, it's either a positive exponent or a negative exponent, based on the direction that we move that decimal. We'll spend some time in class actually working with these scientific notations if you're not familiar with them already. We have this sort of scheme we have evolved to help us deal with or make sense of these very complicated problems, which we're going to call dimensional analysis. But in addition to that, we have this sort of, I have a process we can talk about for answering any problems within this. First step we're going to do is read the question. Make sure we understand all parts of the question, regardless of how long it is. We want to identify what we're trying to solve for. What is the answer we're looking for? We also want to be aware of what we're starting with. What information do we have at the beginning? Right? So once we're clear on what the question is, what we're trying to solve, and what we have at the beginning, we have to devise a method to go from our starting point to our ending point, including any conversion factors that we either know based on the prefixes or that we can look up if it's an English conversion, such as a mile or one of those that we're kind of typically think of here in America. At that point, once we have a sort of a roadmap of how we're going to go from what we have to what we want, at that point we set up our equations and put numbers down. At this point, we're going to check to make sure our units cancel. If our units cancel from the beginning to the end, giving us the units of the answer we want, then we're pretty much guaranteed that our solution is going to be correct. And we can go ahead and solve this equation. At this point, we have 2 more steps. We want to look at that answer, the solution that we have, and does it make sure it makes sense? Is it the right size that we would expect for that unit? Is it are the units correct? And finally, does that solution answer the question we had at the beginning? So if we follow this sort of set of rules, we should be able to answer a question whether we understand the underlying chemistry or not, right? If we just follow these simple procedures. For example, let's look, if we have a diameter of a single carbon atom is 154 picometers, how many atoms would be in a line of 100 millimeters long, which is equivalent to about the length of or the diameter of a human hair. So that's a lot of stuff we haven't talked about yet. Carbon atoms, hairs in there. But if we just sort of follow that, work that plan we've established, look at with what we have to where we want to go, we can answer this problem or solve this problem. So we're given a total line length of 100 millimeters. Right? And somehow we have to relate that to the number of carbon atoms that we would fit in that line. Right? The unit we give for the line is 100 millimeters. We can convert that to meters, right? Because that's our base, sort of our base unit for length. And then we can go to this sort of the size of the carbon atom, which is in the picometers. So we can do that conversion. If we know how long that line is in picometers, we should be able to figure out how many atoms will be equivalent to that line. So that's the process that we're going to take. At the bottom here, you can see that worked out as an equation. We start with what we have, put in the conversion factors to go from millimeters to meters, making sure that the numbers that are the units cancel out. So if it starts off with millimeters on top, we would want to put the millimeters on bottom. So essentially multiplying by fractions here. So things on the bottom and top cancel each other out. We can work that through until we're left with atoms. So if we solve that mathematically, we figure out that we get 6.49 times 10 to the 8th atoms is equivalent to a 100 millimeter line. Right? Does that make sense? The picometer was really small, right? 10 to the minus 12. A millimeter is much bigger than that. So if we have something that's big, it's going to take a lot of those small units to equal that bigger line. And that makes sense. We have 10 to the 8th, so about a billion of those carbon atoms is going to equal that length of line. So that the magnitude works out. We're left with atoms. That's what we wanted to solve. So it looks like we've answered this problem correctly. We can then go on and take that a little further and say, what is the mass of the line if a single carbon atom weighs 1.993 times 10 to the negative 23 grams? Again, we want to go from the mass of an atom to the mass of the line. And this time it's only going to take a single conversion because we know the mass of a single atom. So if we do this problem, we see that we get 1.2 times 10 to the negative 23 grams is what that 100 millimeter line would weigh if it was made up of those 6.49 times 10 to the 8th carbon atom. So even if we don't understand the words that are in the problem or the underlying chemistry that involved, if we follow our units in this dimensional analysis scheme, with what we start with to what we end with, or what we want, then our answer should be correct. So these are the types of problems that we're going to be doing from now until the end of the semester. We're just going to be doing some conversions, following this same type of dimensional analysis setup.